This is my tiny PCB motor, and for the last 5 years I have been trying to make it stronger and faster. But here's the twist. The motor is just half of the problem. So in this video I'm going to build 4 different controllers, test which one is the most efficient and try to make it smaller. My goal is to use this research to select a new controller for my PCB rover and also explore the possibility of other exciting projects along the way. So let's start by understanding how an ESC works. My PCB motor is like a brushless motor. It has 3 phases. The only difference is that these coils are integrated inside the stem PCB. To simplify things, imagine the rotor being like a merry-go-round and the stator is like my hand trying to spin it. The switching controls the speed. So by turning on and off the coils, they can turn a magnet on top. There is a total of 6 steps, and for each step there will always be one phase connected to VCC, another to ground, and one that is floating. This is what's called a 6-step trapezoidal waveform, and a microcontroller can help us generate these signals to rotate the rotor. These signals will have to pass through a gate driver to switch 6 transistors, and a driver like this one has everything inside, which is ideal for my low power motor. Now the problem here is that the controller is running blind. One timing mistake will make it lose synchronization, so next we need to find a way to read and control the speed, and there's 2 ways how we can do that. The simplest one is to put a magnetic sensor near the rotor. This way it can detect the polarity changes of the magnets inside the rotor. The rotor has 8 magnets, so from just one sensor we can determine the RPM. From this value the microcontroller can make small adjustments in time to sync the speed. I confirmed the speed with a laser tachometer. That is why I had to paint the rotor black and put a piece of reflective tape on it. The maximum speed I measured was around 3500 RPM, so this ESC has a lot of limitations. It's the same one I used in my last project, and apart from the poor speed performance, it also gets quite hot. Both of these issues can be fixed by using a more powerful microcontroller, but why bother when we can just replace everything with a single chip? This code-free solution can directly drive the motor, generate its own 6-step commutation waveform, and control the speed from the onboard sensors. So it will kind of do the job of these 2 chips. At first I tried to order some development boards for this chip, but they were quite expensive, so it made more sense to open Altium and design my own board, putting the stator on the same PCB and add the sensors close as possible to the rotor. If you'd like to test this development board yourself, the files are available for free, and you can also download Altium Designer and 365 from the link in my description. One disadvantage of this chip is that it requires 3-hole sensors instead of 1. I added a bunch of pins because it can communicate with multiple interfaces, but it only requires 1 to adjust the speed using the duty cycle. Whoa. The maximum unloaded speed I read with the tachometer was 33,900 RPM. It's going way faster than I thought it would. That's very stable. The speed did drop when I increased the load, but I was still impressed, especially because the motor was operating at much lower temperatures. This is because the duty cycle of the 6-step waveform is being adjusted based on the motor's load. In fact, it draws less power without a load. There are still some drawbacks with the specific design. The first one is that the motor cannot be powered with a 1-cell LiPo battery, because it's more intended to be used in cars. Besides this, we also have the extra cost of the 3-hole sensors. These take up a lot of space considering the size of the motor, which might be unacceptable for some applications like this one. This tiny propeller is integrated into the rotor and made from aluminium. I don't have a 5-axis CNC, so I got it made as PCB way. I was very disappointed because it just reached 6000 RPM. The rotor is lighter than the wheel, so most probably this is happening because of drag. The extra area of the sensors is also blocking most of the airway, so this is a very poor fan. To solve this, I can either add more layers and place the whole sensors directly underneath the coils, or keep the original design and go sensorless. High-speed brushless motors usually use these type of sensorless controllers. So I want to start by designing my own from scratch and then try to simplify it. I'll be using the same hardware I used for the version 4 PCB Motor project. This ESC supports both sensored and sensorless control, but I never tackled the sensorless part because the rotor was still just too wobbly. I only had one of these prototypes, which I broke for the intro. So thank you PCBWay once again for sponsoring all these PCBs. As I said before, to drive a 3-phase motor, you always need to have a pin that is connected to VCC, another to ground, and one that is floating. And as the rotor spins, this undriven phase starts generating a voltage, which is known as back EMF. The signal is directly proportional to the motor speed, and its midpoint voltage is known as the zero crossing point. Detecting this point can help us determine the timing needed to keep the motor in sync, while also controlling its speed. This is not an easy task to do because any delays in the code will result in the loss of synchronization. This is why this ESC has a much more powerful microcontroller than this one, as it is specifically intended to drive high-speed brushless motors. Now the first part of this algorithm involves driving the motor in open loop to get the magnet spinning and generate back EMF in the coils. While we do this, it's very important to start lowering its duty cycle. This duty cycle is going to act like a speed percentage, so in open loop we want it to be as low as possible. As soon as the motor gets in sync, we can start increasing it, and this automatically increases the speed of the motor. This high frequency PWM will introduce noise to our back EMF waveform, so I added a capacitor to smooth things out and a potential divider to bring the signal down to the microcontroller's voltage level. Tuning these three capacitors is one of the key elements of this project. Setting the value too large can attenuate the signal or introduce a phase shift. The reason why I know all this is because I have already worked on a similar project a long time ago, but this motor was a different kind of beast. Its phase resistance is very high compared to other brushless motors, and it barely generates any back EMF, so I wasn't even sure if it would work. This could have been a complete waste of time. In fact, it took me weeks trying to tune the open loop algorithm to get it to spin fast enough to detect back EMF. I ended up spinning the motor to 11,000 RPM in open loop, but the sensorless algorithm still wasn't stable. So I kept testing the software until I found that one of the ADC channels was sometimes outputting garbage data. I managed to fix this problem with just a while loop, and this immediately showed a sign of improvement. But the motor still wasn't holding in sync. So then I did some software filtering and averaging to help the motor out. But the main issue was that the two back EMF slopes wasn't symmetrical. I decided to ignore one of them and base my timing on this one point.
If this doesn't work, I think I'm just going to give up. Oh my god, I think it's working.
The motor was spinning faster than 33,000 RPM. At this maximum speed, the back EMF was getting a bit saturated. I didn't understand completely why this was happening, but at least it was stable and not getting caught. It also managed to spin the wheel to around 22,000 RPM and the propeller to 18,000 RPM, which was very impressive. It isn't that visible in the footage, but some smoke was getting exhausted out. The only problem I was left facing with this controller is the startup sequence, because both of the wheel and propeller wasn't always switching to the sensorless algorithm. This means that I have to either customize the open loop algorithm specific to the load or add current sensing. But to do that we need more real estate on the board, which brings us to the next point. As fun as this engineering challenge was, this ESC doesn't really make sense in my mind. It's just too big for the motor. So the next step is trying to make it smaller. One-chip sensorless controllers are far more common than sensored ones, as their most popular applications are low-power brushless fans and laptops. Most of these controllers are usually designed to operate with standard motor parameters, so I wasn't sure that they would work with my PCB motor's high phase resistance and low back EMF. In fact, from the 3 development boards I tested, only one chip worked, and it still involved some tuning. This specific chip required an additional pin connected to the midpoint of the phases. Soldering a wire directly to this point didn't work that well, but simulating it with 3 resistors did. According to the datasheet, this is still okay to do. However, its speed still wasn't that high, so I decided to try it out on a PCB to see if it will improve. But nothing really changed. This chip was also limited to rotate the rotor in just one direction. So I made some more research and found this chip which supports both clockwise and anti-clockwise rotation. It was a bit of a gamble designing this one with my PCB motor because there were no development boards available to test it out on, but the results were completely surprising. It didn't beat the 33,000 RPM high score, but both the wheel and propeller rotated just as fast as my sensorless ESC. It seems that the algorithm it's using is a little bit different from the one I use, because it's switching the PWM off at the midpoint to avoid filtering, which I think is quite neat. This ESC also requires a common point, and its datasheet doesn't mention any simulation resistors, but I am using them here. So I tried to remove these resistors and soldered a wire directly to this point, and it worked just as fine. So technically these 3 simulation resistors can be eliminated, which makes the ESC even smaller. The only thing that sucks about this chip is that it has a 5-second lock timeout, which might not be acceptable for some applications. The exposed copper heatsink did manage to keep the motor cooler because air was passing through the vias, but it was also blocking the exhaust. So I decided to connect a non-heat-sinked PCB motor to this tiny controller, which had the same circuit, and this turned it into a little PCB motor fan. This ESC is practically weightless, which is ideal when you start thinking about rust. 4 of these motors can only theoretically lift around 5 grams, so we still need a little bit more thrust to make a PCB drone feasible. But I have a feeling that we can juice more power from it by redesigning the propeller and the motor. Remember that in the past my PCB motor's performance was limited by temperature, so it was designed not to get hot at low speeds. And now it's pretty clear that at high RPMs temperature is no longer a problem. I think it's important to start differentiating between high RPM and slow RPM PCB motors. The sensorless ESCs are not going to work at slow speeds because the motor doesn't generate back EMF. The sensor chip also doesn't have a slow speed limit, so I think the best option to drive the motor slow is by using a custom controller. If we use the same algorithm, it still makes the motor spring quite a lot, but if we replace this square wave with a sinusoidal one, it makes things much more smoother. Anyways, for now I will just focusing on redesigning the motor for high-speed applications. If you don't want to miss that, remember to subscribe and check out these other 2 videos if you want to learn more about PCB motors. Special thanks goes to all my Patreons who directly supported this research. Feel free to join if you want to get a glimpse of my upcoming projects.